Deep inside the armored casing of a modern turbofan engine, there exists a specific zone.
This is the High Pressure Turbine. Here, the conditions are not merely extreme, they are apocalyptic. The air in this chamber is screaming. It has just detonated in the combustor, expanding violently, and is now rushing. The pressure is crushing, squeezing the air with 40 times the force of the atmosphere at sea level. But the true killer is the heat. The temperature in this section climbs to 1,700 degrees Celsius. To put that number into perspective, it is not just hot. It is 300 degrees above the melting point of the metal alloy used to build the engine itself. Lava from an erupting volcano is typically 1,200 degrees. The inside of this engine is 500 degrees hotter than molten rock. By every standard law of physics, the turbine blades spinning in this inferno should instantly lose their structural integrity. Yet, they remain solid. They hold their shape. And they do it while spinning at over 12,000 revolutions per minute. At this rotational speed, the centrifugal forces are terrifying. A single turbine blade, that is the equivalent of hanging a fully loaded freight locomotive from the tip of a single blade, while simultaneously heating it to the temperature of a star.
This is the single greatest material science magic trick in human history.
To understand how we achieved this impossible thermal standoff, we have to look past the machine.
The story begins with the fundamental enemy, heat. In the relentless pursuit of aviation efficiency, heat is actually what we want. It is the currency of thrust. According to the Carnot Theorem of thermodynamics, the efficiency of any heat engine is directly dependent on the temperature difference between the heat source and the heat sink. The hotter we can burn the fuel, the more energy we can extract from every single drop of kerosene. This creates a lethal paradox that haunts every aerospace engineer.
The propulsion team is constantly pushing the combustion temperature up to extract more power,
while the material scientists are screaming that the engine is going to disintegrate.
This delicate balance is achieved through ingenious engineering. Tiny internal cooling channels, for instance, divert cool air to the blade's surface.
Further advancements in material science, like single crystal alloys and thermal barrier coatings, create an atomic fortress that can withstand the impossible.
This is how we defy physics, pushing the boundaries of what's possible, one impossible engine at a time.
When jet fuel is atomized by the injectors and ignited in the combustor, the gas expands with explosive force. This high-velocity stream of fire slams directly into the first stage of the high-pressure turbine. This is the critical zone. These blades are the first solid objects the fire touches.
If we used standard steel, or even high-grade titanium, they would not just melt.
Before they even reach their melting point, they would suffer from a catastrophic phenomenon known as creep. Creep is the slow, permanent deformation of a solid material under the influence of mechanical stresses and high temperatures. It is a microscopic surrender. At 12,000 revolutions per minute, the centrifugal load is trying to rip the blade out of its root.
It is pulling on the atoms, trying to stretch the metal structure. If the metal gets too hot, its atomic bonds loosen. The atoms begin to slide past one another.
The blade physically elongates.
In the tight tolerances of a modern jet engine, where the gap between the spinning blade tip and the stationary casing is measured,
blade tips would crash into the casing. This would strip the engine lining, unbalance the rotor, and cause an immediate, uncontained engine failure.
To fight creep, engineers had to abandon iron.
Iron creates oxides that flake off, and it loses strength too rapidly. Instead, we turned to nickel. We created a new class of materials called superalloys.
Nickel-based superalloys, like Inconel, possess an extraordinary ability to maintain their strength even when they are glowing white hot. This is due to a unique crystalline structure, where cubic crystals of one material lock inside the cubic crystals of another.
But simply changing the chemistry was not enough. We had to change the geometry of the metal at a microscopic level.
In the early days of jet propulsion, turbine blades were cast using standard methods. You would pour liquid metal into a mold and let it cool.
When liquid metal cools in solidifier, it forms grains. You can imagine these grains like a puzzle.
Under the immense stress of thermal expansion and centrifugal force, these grain boundaries are the weak points. It became clear that as long as the metal had grains, it had a limit.
We stopped casting blades with random grain structures. First, we introduced directional solidification, aligning the grain.
The ultimate breakthrough was the single crystal blade. To create a single crystal blade, we do not just pour metal, we grow it. The process takes place in a vacuum furnace to prevent any reaction with oxygen.
The molten superalloy is poured into a ceramic mold that has been preheated to the exact temperature of the liquid metal. Then, the mold is slowly withdrawn from the furnace, millimeter by millimeter. At the bottom of the mold, there is a geometric filter. It is a corkscrew shape, often called a Pig Tail Selector. As the metal at the bottom begins to cool and solidify, many crystal grains start to form and race upwards.
They enter the helix of the pigtail.
Because of the spiral shape, the grains collide with the walls of the passage and are blocked.
Only one single grain, the one perfectly oriented with the vertical axis, manages to survive the spiral maze.
This single survivor emerges into the main cavity of the blade mold. As the mold continues to lower, this one crystal acts as a seed.
It grows, it expands, it fills the entire void.
The entire turbine blade, every curve, every internal channel, every mounting route, solidifies as one single.
There are no grain boundaries. There are no microscopic weak points for the heat to attack.
This single crystal architecture gives the blade immense strength against creep, allowing it to survive temperatures that would tear a standard metal apart.
However, we must return to the numbers. A single crystal superalloy melts at roughly 1,400 degrees Celsius. The gas coming out of the combustor is 1,700 degrees. The physics still says the blade should die. The metal is strong, but it is not invincible. To bridge this 300-degree gap, we have to cheat thermodynamics. We have to insulate the metal. This leads us to the second line of defense, the thermal barrier coating, or TBC. The blade is sprayed with a ceramic material, typically yttria-stabilized zirconia. We choose ceramics because they are incredible insulators. Think of the tiles on the space shuttle, or a coffee mug.
By applying a layer of this ceramic that is less than half a millimeter thick, we can create a temperature drop of up to 150 degrees Celsius across the coating. But there is a catch. Ceramics are brittle. Metal is ductile. As the engine heats up and cools down, the metal lids. To prevent this, engineers apply a bond coat, a metallic glue that bonds the ceramic to the superalloy.
We now have a super strong single crystal protected by a ceramic blanket.
The final and most sophisticated defense is to turn the blade itself into a cooling system. Look closely at a modern turbine blade. It is not a solid piece of metal.
It is an intricate heat exchanger. Inside, serpentine passages snake from this air bypasses the combustion chamber entirely. It is piped around the engine core and pumped into the base of the spinning turbine blades.
This air, roughly 700 degrees Celsius, sounds hot to us. But compared to the 1,000,
it is 1,000 degrees colder than the environment. This air rushes through the internal passages, scrubbing the heat away from it.
To make this heat transfer more aggressive, the interior walls of the blade are lined with turbulators. These are tiny. They trip the airflow, turning it from a smooth laminar flow into a turbulent, chaotic mix. This turbulence forces more air, pulling heat away faster and carrying it out of the blade. But the real genius happens when this air leaves the blade. The surface of the blade is drilled with hundreds of microscopic holes. They are shaped, angled diffusion holes, drilled by lasers or electrical discharge machining. As the internal cooling air pushes out through these holes, the angle forces it to lay flat against the surface of the blade. It creates a thin film of cool air that sticks to the exterior of the metal. This is called film cooling.
The superheated combustion gas never actually touches the blade or the ceramic coating directly. It glides over this sacrificial layer of air.
This is a delicate aerodynamic ballet. If the air shoots out too fast, it will penetrate the main gas stream.
If the air shoots out too fast, it will penetrate the main gas stream, blow off the surface, and mix with the hot gas, becoming useless.
If it comes out too slow, the hot gas will override it and burn the surface. It has to be perfect.
The momentum flux ratio between the coolant and the mainstream gas is calculated to the decimal point to ensure that the film stays attached. This incredible engineering allows turbine blades to operate in extreme heat, continuously pushing the boundaries of flight and power generation. From the smallest turbulator to the precise film cooling, every detail contributes to the efficiency and safety of modern aviation. It's a testament to human ingenuity, pushing the boundaries of what's possible, one perfectly cooled blade at a time. The manufacturing precision required here is absolute.
If a few of these cooling holes are blocked by dust or sand, that specific spot on the blade will lose its film protection. The temperature will spike instantly. The metal will soften, bulge, and burn through in seconds. This is why volcanic ash is so dangerous to jet engines.
It melts in the combustor and then resolidifies on the turbine blades as glass, blocking these cooling holes and suffocating the engine's thermal defense system.
We must also consider the coating of the cooling passages themselves. In the newest generations of engines, like the GE9X, we are seeing the introduction of ceramic matrix posits. CMCs are a woven fabric of silicon carbide fibers embedded in a silicon carbide matrix. They are 1/3 the weight of metal and can withstand temperatures hundreds of degrees higher without needing as much cooling air. This is critical because every ounce of air we bleed from the compressor to cool the turbine is air that is not being used to generate thrust. The more heat-resistant the materials are, the less air we need to waste on cooling, and the more efficient the engine becomes. The interplay of these technologies creates a system that operates on the razor edge of failure. Rotation speed creates a centrifugal pull of thousands of Gs. The gas loads try to bend the blade backwards.
The thermal gradient tries to tear the coating off. And through it all, the blade glows, spinning in a controlled explosion, surviving an environment that should turn it into a puddle.
Engineers are currently experimenting with environmental barrier coatings to protect the new ceramic composites from water vapor attack.
We are looking at additive manufacturing, or 3D printing, to create internal cooling channels with geometries that...
The modern jet engine is not just a machine. It is a testament to our refusal to accept the limits of materials. We force metal to survive where it shouldn't. We force air to act as a shield. We manipulate the atomic.
Every time you hear the roar of a jet engine, remember that inside there is a battle being fought between the crushing.
We are winning that battle, but the margin of victory is measured in microns and single degrees.
To keep deconstructing the world's most complex systems and understanding the physics that keeps them alive, stay connected to Gridonix.